Everyone, I am student of Sri Venkateshwara College of Engineering, Bangalore. My name is A. Purnasesyan, Department of Information Science and Engineering, Academic Year 2022-26. The main topic of our presentation is corrosion. Corrosion is nothing but rusting of iron. Anything cannot be permanent in this world. As the same way, iron cannot be the same as when it is manufactured. It has to go under rusting and it has to be destroyed. Let us see what exactly corrosion is. Corrosion can be defined as the destruction or deterioration or loss of metals or alloys by the surrounding environment through chemical or electrochemical reaction. In simple terms, it is called as rusting. So let us see the reaction for rusting of iron. Fe2 plus 2OH minus give rise to FeOH twice, which is called as ferrous hydroxide. This ferrous hydroxide, which in turn reacts with oxygen and water, gave rise to Fe2O3.3H2O. This Fe2O3.3H2O is called as hydrated ferric oxide, nothing but rust. Let us see the mechanism of rusting of iron. Iron undergoes oxidation and give rise to Fe2 plus 2 electrons, where Fe2 plus is nothing but iron ions and 2 electrons is liberating 2 electrons. And water is treated with oxygen and give rise to hydroxyl ions, which undergoes reduction. This is a simple mechanism for the rusting of iron. Let us see the electrochemical theory of corrosion. Electrochemical theory taking iron as example. According to electrochemical theory, when a metal such as iron is exposed to corrosive environment, following changes occur. A large amount of tiny galvanic cells with anodic and cathodic regions are formed. At the cathodic region, oxidation reaction takes place and the metal gets converted into its ions, liberating electrons. Conjugately, metal undergoes corrosion at the anodic region. At the cathodic region, reduction reaction takes place. Since the metal cannot be reduced further, metal atoms at the cathodic region are unaffected by the cathodic reaction. Nothing but, according to electrochemical theory, when iron is exposed to an environment, a small amount of galvanic cells are surrounded around it, such that when these galvanic cells are surrounded around the metal, anodic and cathodic regions are formed. As we know that anodic region undergoes oxidation. This oxidation takes place at the metals and it gets converted into its ions. When metal gets converted into ions, it liberates some amount of electrons. Consequently, metal undergoes corrosion at the anodic region, whereas at the cathodic region, reduction reaction takes place. Since the metal cannot be reduced further, metal atoms at the cathodic region are unaffected from the corrosion. Let us see the anodic and cathodic reactions. At the anode, oxidation takes place, in which the metal atoms are converted into their ions, liberating electrons. For example, Fe gives rise to Fe2 plus 2 electrons. At cathode, the cathodic reaction is based on the nature of the environment. Firstly, in the absence of oxygen, that is nothing but liberation of hydrogen. In acidic medium, liberation of hydrogen takes place. 2H plus 2 electrons give rise to H2. In neutral or alkaline medium, hydroxyl ions are formed with simultaneous liberation of hydrogen. 2H2O plus 2 electrons give rise to 2OH minus plus H2. Let us see the cathodic reaction in the presence of oxygen. Absorption of oxygen, nothing but absorption of oxygen. In acidic medium, absorption of oxygen takes place. 4H plus O2 plus 4 electrons give rise to 2H2O. In neutral or alkaline medium, hydroxide ions are formed. 2H2O plus O2 plus 4 electrons give rise to 4OH minus. Then the iron formed from anode combine with hydroxyl ions from cathode to form iron hydroxide on the surface between anodic and cathodic area. Fe2 plus 2OH minus give rise to FeOH plus, which is nothing but ferrous hydroxide. This ferrous hydroxide or iron hydroxide. This iron hydroxide further reacts with oxygen and water, forming hydrated ferric oxide, which is a corrosion product rust. So, 4FeOH twice plus O2 plus 2H2O give rise to 2Fe2O3.3H2O, which is called as hydrated ferric oxide or rust. Now let us see the types of corrosion: differential metal corrosion and differential aeration corrosion. Differential metal corrosion. Differential metal corrosion occurs when two dissimilar metals are in contact with each other and exposed to a corrosive conducting medium. The metal with lower electrode potential acts as anode, undergoes oxidation and gets corroded, and the other metal with higher electrode potential acts as cathode, undergoes reduction and protected from corrosion. This type of corrosion is known as galvanic corrosion or differential metal corrosion. So, in differential metal corrosion, for example, let us take two dissimilar metals like iron and tin. In these two metals, iron is having lower electrode potential and it will act as anode and undergoes oxidation. Oxidation is nothing but liberation of electrons. So iron gets corroded, and other metal which is tin with higher electrode potential acts as cathode and undergoes reduction. So in reduction process, the metal cannot be reduced more further and it is protected from corrosion. This type of corrosion is known as differential metal corrosion. So in the differential metal corrosion, the rate of corrosion depends mainly on the difference in the potential of the metals. Higher the difference, faster is the rate of corrosion. Let us see the anodic and cathodic reactions. At anode, any metal such as, for example, let us take M. It gives rise to Mn plus electrons. At cathode, reduction reaction takes place depending upon the nature of the environment. 2H plus 2 electrons give rise to H2. So this is the example which we have discussed before. Iron, which is having lower electrode potential, acts as anode and undergoes corrosion, liberating electrons. Whereas tin, which is having a higher electrode potential, acts as cathode and it is not affected from the corrosion. Now let us see differential aeration corrosion. In differential aeration corrosion, when a metal is exposed to different concentrations of air or oxygen, part of the metal exposed to lower concentration of oxygen becomes anodic and undergoes corrosion, whereas the other part of the metal exposed to higher concentration of oxygen becomes cathodic and remains unaffected. This kind of corrosion is called as differential aeration corrosion. For example, let us take an iron rod which is partially immersed in NaCl solution. Part of the metal which is immersed in the solution is exposed to lower concentration of oxygen. As you know that in water, water consists of dissolved oxygen which is less than the oxygen than the outside environment. So, due to so when iron rod displaced immersed in NaCl solution, part of the metal immersed in the solution is exposed to lower concentration of oxygen, becomes anodic and undergoes corrosion. Whereas part of the metal outside NaCl solution exposed to more concentration of oxygen becomes cathodic and remains unaffected. Let us see the anodic and cathodic reactions of differential aeration corrosion. At anode, iron undergoes oxidation and liberates electrons. That is, Fe gives rise to Fe2 plus 2 electrons. At cathode, water undergoes reaction and forms hydroxyl ions. 2H2O plus O2 plus 4 electrons give rise to 4OH minus. And the net cell reaction is Fe2 plus 2OH minus give rise to FeOH twice. That is nothing but ferrous hydroxide or iron hydroxide. Here is a small diagram which shows the differential aeration corrosion. When I met iron rod dipped in NaCl solution, you can see that there is a lower concentration of oxygen inside the water. Because of that, iron undergoes corrosion which is inside the water, and the iron outside the water is free. It is unaffected from the corrosion because it is exposed to more concentration of oxygen and acts as cathode. So this is all for today. So we have discussed about corrosion, electrochemical theory of corrosion and types of corrosion. If you have any doubts, please don't forget to comment.